Hello friends, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture I am going to give a few numerical problems based on equilibrium under the chapter Newton laws of physics. In the last chapter I have also discussed the concept of equilibrium, how the net forces on an external object is zero, and if the total external forces on an object is zero, then the system is in equilibrium, right? If you don't know about the theory of equilibrium, you can visit my previous lecture. I will share the link in the description box, but here too I will explain a little about how we can handle the numericals problem on equilibrium. So in this numerical we have a situation in which we have three ideal strings and a block of 40 kg with specific angles. We need to find the values of T1, T2 and T3, that's the tension forces in the strings. Okay, so in this numerical, let's say this joint is known as A, right? So this point A is at a rest under the three tension forces which are applying on this joint, and the block is also at rest. So let's discuss about the block. For the block, as we can say, it's a 40 kg block, so it is under the gravitational pull of mg and a tension force is acting upward T1. Okay, so it has some mass 40 kg, so the block is at rest. It means that the total upward force is equals to total downward force. It means T1 equals to mg. So T1 comes out to be m equals to 40 kg and g equals to 10 meter per second square. It comes out to be 400 Newton. So this is the value of T1. Okay, it's quite easy. Let's calculate the values of T2 and T3. So to calculate the value of T2 and T3, we need to resolve them. So T2, as it will act in this direction, and T3 act in this direction. If we taken from point A, we will resolve it into components. So one of the component of T2 is in this direction, that is T2 cos of 53 degree, and one is in the upward direction and we call it T2 sine of 53 degree. 53 degree. Similarly, we will resolve the components of T3, and one of the components is T3 cos of 37 degree, and one is in the upward direction, that is T3 sine of 37 degree. Okay, and here T1 act in the downward direction from point A. Okay, so now along x-axis, for equilibrium, net forces along the x-axis must be 0. It means that there are two forces acting along the x-axis. It means that T2 cos of 53 degree must be equal to T3 cos of 37 degree. This is the first condition, and the second condition is and the second equation we can get from the y-axis. Okay, and from y-axis, this is our first equation, and along y-axis, if we see along y-axis, again net forces along the y-axis must be 0 if to satisfy the condition of equilibrium. So it means total upward forces equals to total downward forces. So the total upward forces are T3 sine of 37 degree plus T2 sine of 53 degree is equals to, so the downward force is T1. Here you can see these two forces are in the upward direction, right, and this T1 is in the downward direction at point A. Okay, so we need to solve these two equations. As we know the value of T1 equals to 400, right, and we can calculate these two equations simultaneously. This is our second equation. Okay, so from equation first, as so to find the values of 37 and 53, we know the triangle. This is 37 degree, this is 53 degree, this is 3, this is 4, this is 5. So sine of 37 degree is nothing but 3 by 5, and sine of 53 degree is nothing but 4 by 5. Similarly, cos of 37 degree 4 by 5, and cos of 53 degree is equals to 3 by 5. Okay, alright, so these values we can use in the above two equations. So the equation first become T2 cos of 53 degree, which is 3 by 5, equals T3 cos of 37 degree. 37 degree is equal to 4 by 5. So we can handle this equation. 3T2 equals to 4T3, because 5 term cancel each other. This 5 and this 5 cancel each other. So from here we can write T2 is nothing but 4 by 3 T3. Let's say this is our equation number third. Okay, we will use this equation third in equation second. Okay, from equation third we have T3 sine of 37 equals to 3 by 5 plus T2, and we know the value of T2. T2 now is 4 by 3 T3. Sine of 53 degree is equal to 4 by 5 equals to T1, and we know T1 equals to 400 Newton. Let's solve this equation to calculate the value of T3. Okay, so it's 3 by 5 T3 plus 16 by 15 T3 equals to 400. Okay, so if we solve this, this comes out to be 15. 9 T3 plus 16 T3 equals to 400. I hope you know how to solve this. So 16 plus 9 is 25 T3 divided by 15 equals to 400. So from here we can calculate the value of T3. So T3 is equal to 400 multiply 15 divided by 25. We can solve this equation. 5 3 15, 5 5 25, and 5 8 40. So it's 80 multiply 3. It comes out to be, so T3 is nothing but 240 Newton. Let's say this is our equation number 4. Now use the equation 4 to calculate T2 in equation third. So put equation 4 in equation third. Equation third is T2 is equal to 4 by 3 T3. So T2 equals to 4 by 3 T3. So we will use the value of T3 here. So T2 equals to 4 by 3 into 240 Newton. So we can solve it. 313, 3824. So 4 into 80. It comes out to be. So this is the value of. So finally we can write T1 equals to 400 Newton. T2 equals to 320 Newton and T3 equals to 240. These are the values. I hope you enjoy this numerical and you understand it how we can easily solve the equations to find out the required variables. In this numerical problem, we have the diagram shown. The system is in equilibrium and choose the correct options. So we are given 4 options. We need to choose the correct option. Which one is correct? So you can see it is a symmetrical diagram across angle theta. So we have 3 objects, A and B blocks having equal mass small m, and block C has capital M mass. So we need to choose the options that which one is correct. Okay, as this is the symmetrical diagram, so let's say I am taking this point P. So let's say this is point P. So about point P, we have two components of the tensions in the upward direction, as at point P the tension is in this direction and in this string the tension is in this direction. So here becomes T cos of theta from one side from this string, and from this string again T cos of theta in the upward direction. So I am drawing two arrows. Okay, so these two T cos theta is acting at point P in the upward direction, and here let's say this is T dash in the downward direction. Okay, so what it means that T dash is equals to 2T cos of theta. This is our equation number 1, and here again we can write capital Mg. So from the block C, this is block C, so here T dash acting upward direction and capital M G acting downward direction. The block C is at rest. It means that T dash is nothing but Mg. So T dash nothing but capital M G. So we can this here. So it becomes capital Mg equals to 2T cos of theta. This is our equation number 2 now. Now from A or from diagram B, we can see here small mg acting downward direction. So from this FPD, from this situation, as A is at rest, it means that the total upward force, which is tension T, is equals to the total downward force acting on A, which is small m g. So from this we can write T is nothing but small m g. This is our equation number 3. We can substitute the equation 3 in equation 2. So capital Mg becomes 2 times of small mg cos of theta. Okay, now we will decide which option will be correct, as cos of theta equals to 1 when theta equals to 0 degree, but according to the diagram theta is not 0, it is acute angle, it is greater than 0 degree but less than 90 degree. So under such situations, when theta is less than 90 degree but greater than 0 degree, in such situations cos of theta, the value of cos of theta is less than 1 but greater than 0. Okay, so it may be 1 by 2, 1 by 3, 1 by 4, anything, but less than 1 or greater than 0. So when we substitute any value in place of cos of theta, so the resultant will be less than 2 mg. If cos of theta is 1, then we can say it becomes 2 mg, but in such situation cos of theta is less than 1, so the product becomes less than 2 mg. So we can write mg equals to 2 mg cos of theta, which is less than 2 mg. So from this and this statement we can write capital Mg is less than 2 times of small mg. When g terms cancel each other, capital M is less than 2 times of small m. So this is the condition. Let us see which option is correct, and we can say the option C is correct. So this is one of the example based on equilibrium. Let us see one more example based on again equilibrium. We have an inclined plane. Example number 3rd, we have an inclined plane like this, and the inclination angle is 30 degree, theta equals to 30 degree. We have a block of 1 kg, it is 1 kg block A, which is attached with a string, and here we have another block B having mass 2 kg, and this system is attached with a pulley here, and here we have third block C. Okay, the pulley is smooth, the string is ideal, and the surface is frictionless. So I am writing here pulley is smooth, yeah, pulley is ideal, string is ideal, and surfaces are smooth, there is no friction anywhere. Okay, so this is the situation, and we need to calculate the mass of C if the system is at rest. So calculate the mass of block C if the system is at rest. So this is our problem. Let us solve this. So there are actually two strings here, T1, and in this is second string having tension T2. As we know the concept of tension, the tension is always away from the joints in this direction. Here the tension is in this direction, and here the tension is in this direction, that is T2. Okay. So let us draw the diagram, free body diagram for A. As A is something like this, A, block A, and this is angle 30 degree. So a tension is acting T1 in this direction, but gravitational force mg is acting in this direction. We can resolve this gravitational force into its component. One of the component along the surface, which is called mg sin theta, and one is perpendicular to the surface, which is called mg cos of theta. So along the surface, if we see, there are two forces acting on the block A, that is mg sin theta, and in the opposite direction, that is tension, and due to these two forces the object A is at rest, right, the system is at rest. So A is at rest. What it means? It means that mg sin of theta equals to T1. Okay. So this is our equation number 1. So mg sin of 30 degree equals to T1, m equals to 1 kg, g equals to 10, and sin 31 by 2 equals to T1. So it is become T1 comes out to be 5 Newton. Okay. Now, in the same way we can calculate the value of T2 from the free body diagram of B. So, this is object B. Here T1 is acting in this direction and T2 is acting in this direction. You can see the diagram here, T1 and T2. Again mg, gravitational force is acting on the block, gravitational force mg is acting in this way. So, we can resolve the components along the plane, as this is angle theta, along the plane it is mg sin theta, this component will be along the plane, and perpendicular to the plane it is mg cos of theta, right. So, along the surface we have two forces, these two forces along the plane, and in the opposite direction we have T2. As the block B is at rest, it means that T1 plus mg sin theta must be equal to T2. So, from this situation we can write the equation T2 is nothing but T1 plus mg sin of theta. Okay. We know the value of T1, T1 equals to 5 Newton plus the mass of block B is 2 kg, g equals to 10, again sin 30 degree equals to 1 by 2. When we solve this, it becomes 15 Newton, 2 and 2 cancel each other, 10 plus 5 15 Newton. So, this is T2, this is T2. Okay. We know T1, we calculated the value of T2, but the question is mass of block C. Let us move toward that. This is block C. We do not know its mass, let us say it is mg, and T2 tension is acting upward. You can see the diagram here. Here mg is downward direction, capital Mg, and T2 is acting upward. Again the block C is at rest. It means that total upward force is equal to total downward force, that is T2 is nothing but mg, but the T2 is equal to 15, g equals to 10. So, 1.5 kg equals to m. This is the required answer of the problem.